So in the last topic, we looked at a model for laminar flow, but we touched on the fact that in reality, many flows are not laminar. And so that lends itself to the question of like, well, what happens when it's not laminar? And when the answer we've given is, well, it becomes turbulent. And unfortunately, turbulent is difficult to describe, and there's not very many successful models for describing turbulence that actually can predict like a lot of different situations. What we do have in physics is a qualitative way of predicting whether a flow will be laminar versus turbulent. And the way we do that is by calculating something called the Reynolds number, and that's what this topic is about. So at the top here it says, given a flow geometry, the Reynolds number can qualitatively predict turbulent versus laminar flow as a function of speed. So oftentimes we're going to be looking at this as a function of speed, or you can also just say like, hey, given a speed and the other aspects of the flow geometry, what's the Reynolds number and what's it likely to be? But definitely one way to look at it is you could say, well, okay, as you increase speed, that's usually what happens in reality. I mean, if you have like a pipe, right? The pipe probably, if it's made out of like, say, copper or even PVC or whatever, and there's, say, water flowing through it, the pipe is not going to change its characteristics much. It's not going to suddenly increase its radius by, certainly not by a huge amount. It might flex a little bit, right? It might change with temperature a little bit, but it's not going to be large, right? But what can easily change is, somebody turns on the tap and suddenly the flow speed needs to increase, right? And so that's the way I like to look at it, is to say like, well, what happens is if you go at a low amount of flow, you might have laminar flow, but as it gets higher, it's gonna turn into turbulent flow. And what's going to happen is that Reynolds number is going to increase. So at some point there's a transition. If the Reynolds number is low enough, you get laminar flow. If it's higher, you get turbulent flow. And anyway, that's what's described here on the key concept slide. This second item here is the most general definition of the Reynolds number based on something called the hydraulic diameter, and we'll look a little bit more into what that is. We're going to more often in this class look at flows through a pipe, as we've kind of already been doing. And for that, the Reynolds number has this formula, which is actually, if you look at it, there's a 2 here, there's an R here, and if you think, well, isn't diameter just 2 times radius? Like, that seems to be what happened here. We'll look in some more detail. There's actually a more detailed definition of hydraulic diameter, and so that might change our view a little bit. But on the other hand, if you just said, hey, replace diameter with 2 times radius, it seems to work, right? And then there's other things in here like the density of the fluid, the speed of the fluid, and the viscosity of the fluid. So viscosity in that sense is another characteristic. The larger viscosity tends to favor laminar flows, lower viscosity tends to favor turbulent flows. And the way that works is because generally below a Reynolds number of about 2,000, you're going to get laminar flow. And above 4,000, you're going to get turbulent flow. Now, these are 2 numbers. You'll see variations on these numbers, and we're going to discuss a little bit of that specifically. But for this class, more often than not, I'm going to regard 2,000 and 4,000 as basically the cutoffs. And in the kind of the values of Reynolds numbers between those two is sort of a nebulous region where you can't really be sure.